Let's take a look at what it takes to program a ROS robot. This video is part 1 of 2 that talk about the core ROS constructs. Here we'll talk about nodes, parameters, and topics. Hi, my name is Sid Faber from the robotics team at Canonical. All robots based on ROS are programmed using a few simple core constructs. So you'll hear these 5 concepts often: nodes, parameters, topics, services, and actions. In this video, we're going to take some time to look at nodes, parameters, and topics. Prerequisites, if you want to follow along with the commands that we'll be using, simply to have a running robot. I'm going to be using robots that are simulated and running ROS Foxy. In particular, I'll use the Turtlesim built-in simulator, and then I'm also going to use a simulated Waffle Pie training robot running in Gazebo. All these robots are going to be running in a LXD container, and then I'm going to connect to them and query them over the network from another LXD container. I find that one of the most fascinating aspects about robotics is the breadth of disciplines that come together in order to build and operate a robot. You've got physics, mechanical engineering, electrical engineering, software engineering. All these play a part. Now, don't get me wrong, it's not as though you need to be an expert in any of these fields to be successful. In many cases, the things we learned in grade school are more than enough to carry us through, although over time we'll be introducing concepts from these different disciplines. One discipline that matters a lot is mathematics, and in particular, discrete math. I mention that here because in the basic ROS constructs, you'll see the concept of the discrete math graph structure. In a graph structure, you have vertices and edges. Vertices are the endpoints, and they are connected by edges. Within ROS, our vertices are our nodes. So within ROS, you create a node, and that becomes your fundamental building block that will connect over time as we design our robots. Nodes are the endpoints. They're the anchors of our design. Nodes are our single-purpose processing module within ROS. So for instance, we're going to use nodes to control things like motors. We'll use a node to gather data from a laser rangefinder and create a sensor feed. So let's take a look at what some nodes look like in our demo robots. We'll begin by starting up our LXD container for our Turtlesim. Then we'll launch the Turtlesim simulator and start up a new terminal window. Connect into the container from that window, and then go ahead and list the existing ROS nodes in the ROS graph. Here you can see there's one node currently. Let's fire up the teleop key, the keyboard control for the Turtlesim, and see what the graph looks like then. As you see, now we have 2 nodes, one for the simulator and one for the controller of the simulator. Let's look at the same thing in the Turtlebot simulator. So we'll fire up a Turtlebot in a LXD container and then take a look at the nodes that are published by the Turtlebot. Here you can see the node list. It's a little bit more complex than what we saw with the Turtlesim, but still the same principles apply. If ROS nodes are graph vertices, then we need edges to connect them. There's a few different ways within ROS to accomplish this, the primary being through topics. Consider a topic as that edge that connects those 2 vertices, those 2 nodes. Nodes handle the compute, whereas topics broker the communications between the nodes. Topics work on a flexible pub-sub structure. You can always map out the publisher-subscriber pair. There's a data source and a data sink. You can call it a sender and a receiver. You can call it a producer and a consumer. But a node is able to listen or subscribe to one or more topics, and a node will also be able to publish or talk on one or more topics. So topics support this many-to-many relationship. Again, a node can subscribe to multiple topics. A node can publish on multiple topics. Topics and how nodes use them can be statically created when the robot's brought up, or it can be dynamically changed as the robot reacts to its environment. So to borrow a few more terms from graph theory, we're using topics as and nodes to form a directed graph. A robot within ROS is represented as a directed graph. The graph can dynamically change. It can even be separated into subgraphs that may be running on multiple different computers, and they're connected via topics. Let's take a look at how this works in our simulated robots. So once again, we'll begin with our Turtlesim simulator. We'll send that to the background and then start up the Turtle key control node as well. Okay, so you can see the Turtlesim is working. Now let's take a look at what topics exist in our graph. The command velocity, CMD_VEL, is the one we're interested in. That's the one that sends commands for velocity to move the Turtlebot. Let's just use the ROS2 topic echo command to follow what gets sent on that topic. So we're going to subscribe to that topic using the topic echo command. Now you can see as I press a keyboard on the key in the Turtle key, that's actually sending a message out on the command velocity topic. Every time I press a key, another message goes out. Now let's do the same thing with our Turtlebot and see how this behaves in a full-on simulator in Gazebo. We'll go ahead and launch it and then take a look. Here you can see the topics that are published by the Turtlebot simulator. Now let's go ahead and fire up the keyboard control for the Turtlebot. Here you can see how this behaves when we control the Turtlebot with our keyboard. Let's use the topic echo command again to watch what's actually sent on the command velocity topic. One thing that's a little bit different here is that the command velocity topic constantly sends twist messages, sends these messages out at a standard frequency. It doesn't just send them out when a key is pressed. You can see that gives us a nice smooth control over the robot, allows us to move it around the simulated area. A node can publish data on a topic. A node can subscribe to a topic to receive data. But how is the data itself formatted? It's formatted as a message. ROS message structures define how data is exchanged between nodes on topics. There are a few different built-in message types: strings, numbers, booleans, the kind that you'd expect. And it's also possible to combine these into more complex message structures. Many of these common message structures exist as templates within the ROS standard libraries, but you can also create your own message types to suit your needs. Within ROS, the message types are predefined. They are not generally defined on the fly. This means that if you're running a distributed ROS system across a network or on multiple machines, that all the machines have to have the consistent message definitions in order to properly encode and decode data. We'll cover messages in more detail at another time, but for now, let's just explore the message types in some of our topics. If we simply add the -T switch to the ROS2 topic list command, we can see what type of messages are being sent on each topic. In our case, this is a twist message that's being sent on the command velocity topic. Let's take a look at one additional concept related to ROS nodes, and that's parameters. Parameters are what you'd think: your name-value pair, an attribute for a node. Topics do not have parameters, only nodes. Think of a parameter as a configuration item. So for instance, in a robot, you might have a parameter that defines the number of eyes, the number of ears, the number of limbs on the robot. These items are typically set when the robot starts up and rarely change. On the other hand, a topic would be used to show what the eyes see, what the ears hear, where the limbs are actually positioned. And those are changed and they're used to stream data throughout the lifetime of the robot. Parameters are primitive types. They are not complex message types. They're integers, floats, booleans, and so on. Let's take a look at the parameters in our Turtlesim. We can use the ROS2 param list command to show the parameters that are exposed by a node. If we look at the Turtlesim, there's 4 parameters there. One of them is actually related to the simulator, the use sim time. The ones we care about are the background, red, green, and blue. Use the param get command to read a parameter from our simulator. Suppose we want to change the value of our background green component from 86 to 255. We just simply change a param get to a param set and we're good to go. Another really handy option is to set the parameters when we start our robot. We can do that using the --ROS args option and then the -p switch to specify the parameter value. We covered a number of concepts, so check out the blog linked in the video comments if you need some more details. And we're only halfway there. We have nodes that can be set up with parameters, and we could string them together with topics and flow data between them. We still need to discuss services, which are a way to get your robot to perform some activity. We also want to cover actions, which are an asynchronous call to define a goal-driven behavior for a robot. But more on that in our next video. Again, my name is Sid Faber from the robotics team at Canonical. Thanks a lot for watching.